Okay. Hi, Professor. Here is Momon Zhang, and I'm going to introduce the multiple independent relief feeding canal simulator research based on advanced salmon sciences methods. Let's going to start it. So, why I choose the relief feeding canal? Why I choose SoS relief feeding canal because it's really essential in canal modeling, and it is more operatable and more efficient than field test. And at the meantime, it is more economic cost can really be great reduced. And the some sciences algorithm has been widely used. And then it comes out really a lot of novel ideas of based on the SOS algorithms. So what is the background research? So it has been Jack's and Clark's model, and Jack's model is the simplification of Clark's model, but it is not Watson stationary. So pop values, and it's just proposed a random phase for low frequency oscillator. And it's just solved the problem. It becomes Watson stationary. And then Jones' model proposed and he just introduced the random parameters to make up for shortcoming of deterministic canal simulator. And it really improves the independence of the in-phase and quadratic component, but it does not take the physical mechanism into consideration. So what is the SOS methods and how to classify these methods? And the SOS methods just finite sciences, superposition, approximate Gaussian process. And classification can depend on the parameters, and it is the Doppler frequency, Doppler amplitude, and initial phase. And it can be divided into two types of model. The first one is deterministic model. It has unchanged parameters. And the second one is statistical model. It just has the random parameters. And what we focus on? So we study two papers specially. And the paper one just study the statistical model, and it focuses on initial phase phi n, which phi n just uniformly distributed among 0 to 2 pi. Because the fading phenomenon is the phase change with time duration, so the paper one just studied the initial phase impact. And the paper two focused on the deterministic model. And it means that the parameter does not change at all. And it just focuses on phi n, Cn and alpha n. Cn is the path amplitude random variable, and alpha n is the angle of sciences, and the phi n the phase, the Doppler frequency does not change. And for, okay, the paper one just studied the statistical model, and it comes to the condition of effective canal simulators. It generates, here is a condition about theta c and what's just be like this, a condition, and it can generate multiple independent relief feeding waveforms with slight modifications, and the equation gives here, and then comes to the, the simulation. Okay, for other results, an efficient simulator for multiple independent relief feeding form is achieved. We also refer to as modified Jones model. In figure 4, and the results show the autocorrelation of the in-phase component for each waveform, the cross-correlation between in-phase component of the first waveform and the real or imagery part of the second waveform match the desired one really well. And figure 5 indicates that the cross-correlation between two direct complex value random process is 0. the autocorrelation of the complex envelope for the two waveform exactly match the reference model. And as a consequence, the complex value random process satisfies the conditions and the relay fitting spectral requirements as independent relay simulator. Moreover, the statistical properties of the modified model converge to the desired property even when we do over several simulation trials. Yeah. And for the paper 2, it studied the deterministic model. The relay fitting process is based on the generation of uncreated Weiss-Gaussian noise process. SoS simulation model is formed by the sum of finite multiple sensors having some parameters just as Doppler frequency, amplitude, and initial phase that are properly selected to accurately reproduce the desired statistical properties. In phase components, mu I and quadral component mu t and single waveform mu q and single waveform can be expressed as here. Give the equation just like this. This is the waveform, can be divided into quadral component and in-phase component. And then when n approaches infinity, the envelope of SoS simulation model is really distributed. The autocorrelation function, the complex waveform, and cross-correlation function of the two orthogonal components are given by the right side equation. So the paper 2 proposed an improved relay fitting model. How do he achieve this goal? So we studied that, and in this paper, the SoS model has this MEA model, Jones model, and our improved relay fitting model. By different parameter selection, we can see that alpha n and Cn just show a little bit of difference here, but it really has great impact on the final simulation. And we can see the alpha n, nk, and the Cn finally in our approved relay fitting model like this. And the autocorrelation function in phase component is deduced as follows. And the other equation can be carried out just like this. So let's continue and look at the simulation. The PDF is different MNN. That is mean simulation is conducted to evaluate the performance of proposed fitting model with the F max equal to 10 Hertz and the probability density function, that is PDF of the proposed model with different M and N showing the contrast with theoretical PDF. It can be seen the PDF of the proposed model match the theoretical model PDF very well when M and N are not large. So the proposed model is not complexity for computer operation. And then the autocorrelation of the three model and the autocorrelation of cross-correlation function of MEA Jones model and proposed model are compared in figure 2 to show the autocorrelation function of the three model where the theoretical reference theory order Bessel function of the first kind. Apparently, autocorrelation of proposed simulation waveform approximate the theoretical value really well. And in the next figure, the cross-correlation of in-phase and quadral component. In figure 3 shows the correlation function of the in-phase and quadral component in single waveform, just like this. That shows clearly. And the cross-correlation of what? Pair of the relay fitting waveforms, okay, shows the autocorrelation function between in-phase and quadral components of pair uncorrelated waveforms. The proposed model is closer to 0 than others. It can be shown clearly in here and here. And so it is independent to generate multiple uncorrelated fitting waveform, which can be used for creating frequency selective fitting channel and MIMO channels. Okay, so here comes the summarize. In this paper, that we proposed two improved sum of sensors fitting model. It can be generated from the sum of finite sensors approximate Gaussian process, though different parameter changes through the different parameter changes adjustment an adjustment, we validate the original SoS algorithm has been greatly improved, just like the simulation. We can see, yeah, the simulation are performed to evaluate the performance of the proposed fitting model. Yeah, the result shows that the statistical characteristic of the improved kernel model are constant with the theoretical analysis. So, okay. Thank you for listening. Thank you. Let me end the recording.